This is my talk on car alarms and smoke alarms, which I will now give in half an hour for the first time, so wish me luck. I'm Dan Slimmon. I'm there on the Twitters. I don't really tweet about ops or logging very much. I mostly just make jokes, so if you like jokes, go for it. I'm the senior platform engineer at an Internet of Things company called Exosite, which is in Minneapolis. Internet of Things, right? So we'll take things, we'll put some internet on them. Like, we recently made a mousetrap that will text you when it goes off, so you can deploy them all throughout your huge building, right? And then you don't have to hire somebody to go check all the mousetraps. So that's pretty fun. And I also worked at another company, right? So basically I'm an ops, so I wear a ridiculous number of hats. And I think that our most important hat as ops people is our data scientist hat. It is most useful to me now that I learned to make visualizations and do statistical analysis in R, because I can find it really easy to convince people that I'm right. Even though sometimes I'm not right, people tend to really believe you when you have flashy graphs, which is great. So this is a talk about signal to noise ratio, which I think this whole conference is about. And it starts with sort of a word problem. Let's say you are in a school district that is asking for people to develop a plagiarism detection system. And so they want to have teachers be able to upload papers that were given to them by students and detect, yes, there's plagiarism, or no, there's not, in bulk or however. Right, so I've created a little logo for your company here, because we all know how important branding is. And so you've got this project called Plagiar, and you're trying to pitch it to the school board. Right, so you tell them, all right, here's what we found out. If there's plagiarism in a given paper, we have a 90% chance of detecting it. And they're like, wow, that's great, 90%. We're gonna catch 90% of the plagiarists. This is amazing. And then, maybe it's not perfect, so it also catches 20% of non-plagiarists, but we're gonna catch 90% of the plagiarists, right? That's really good. And so the school board is psyched about this new project because they have a serious problem with plagiarism in that 30% of the papers in this school district are plagiarized. So that's really great. So they want you to do some research on your thing, and so they ask you 3 questions about it, right? So I've got three little quick math questions here. This one, given a random paper, so I take a paper just out of a stack at random, I don't know anything about it, and I want to know what's the probability that I'll get a negative result from this paper, right? I don't know if it really is plagiarized or not, but what's the probability that Plagiar is going to tell me it is? So I'm going to give you a minute. I'm actually going to time you. Give you a minute to sort of work this out so you can roll these concepts around in your head, remember how probability works, and don't shout it out, but we'll get to the answer in a bit. Just sort of, I don't know, work it out on a computer. You all have computers. I'll be up here making faces. Got it, internet version of that. Yep, yeah, it's just ran just to totally, these are the probabilities, right? So, okay, all right, so you may not have gotten the answer yet, but at least you thought about it a little bit, rolled it around in your head, and that's all I'm really counting on. So I'll tell you the answer later, and you can check see whether that you get the ego boost for that. So question 2. And this one's way easier, so I'll give you 5 seconds for it. What's the probability that Plagiar will detect plagiarism in a given paper? 5 seconds. And you can shout this one out. Hey, yeah, that's right, it's on there. Why did I ask you that dumbass question? That's like such a waste of your time, right? And mine, I only have half an hour. So So why did I ask you that? Well, I want you to compare it to this other one, which is sort of its inverse. Question 3 says, if you get a positive result from plagiar, what's the probability that there's really plagiarism? Which is related. You can see it's just sort of flipping the condition and the result, but it's a more subtle question to answer, and we can answer it with a chart. Now, I was imagining that I was going to be like over here with my hand like showing you parts of this chart, but clearly that's not going to happen, so you're going to have to pretend I'm doing that. So we can take the 100 random papers. This is a representative sample of the papers in our district, and we can color the non-plagiaristic ones blue and the plagiaristic ones green. And that makes sense. Then we can use the other axis of this square to indicate the negatives and the positives, right? So the positives are going to be dark and the negatives are going to be light. We said 20% of the non-plagiarized papers are going to be marked as positive. Okay? We can do the same thing for the plagiarized ones. 90% of those we're going to catch. And so now we can answer question 1 really easily. So question 1 was take a random paper, what's the probability we get a negative? Well, this is where I was going to point. So 7 times 8, so we have 56 of those light blue ones and 3 of those light green ones, so it's 59%. Did anybody get 59? Yeah, you know your probability. All right, so question 2, that one was easy. That was the trivial one. We had the 90% over there on the green. 9 out of 10 of those green ones are dark. Fine. Okay, but now we can answer the really interesting one, and the one that has an effect on our lives as people who get paged by monitoring systems. What's the probability that you're looking at a true positive if you get a positive result from this plagiar system? Okay, well, if you get a positive result, you know you're in one of these dark squares, but you want to know whether you're in a dark green one. So you got to add up all the dark ones and then divide the green ones by that. And there's the formula, plug in the numbers, trust me, those are right, and you end up with 65.8%. I'm going to pause for a second so you can inhale how terrible that number is. It's kind of unintuitively terrible. We were going to be right 80 to 90% of the time. Turns out 34.2% of the time, if a teacher gets a positive from this test, it's going to be wrong. They're going to waste time on it, and they're going to just stop trusting the test entirely. And remember how psyched the school board was about. What a bunch of doofuses, right? They were like, oh, 90%, that's great. Let's do it. And it turns out it's actually almost useless. So we can take these terms. So we can take these ideas and talk about the terms of sensitivity and specificity, which you learn about in med school. Which people learn. I didn't go to med school, but so my fiance is a vet, so she tells me all this stuff, and then I use it in my talks. So sensitivity is the percentage of actual positives that your test will identify as positive. Right. So we want that to be high, and specificity is another thing that we want to be high. It's the percentage of negatives that you're going to identify. To put it in a more mnemonic way, think of the most sensitive person you know. If you tell them any bit of bad news, they are going to freak the fuck out reliably every time, right? So that person is very sensitive, like a sensitive test. And the other good thing you can be is specific, where your test is only going to detect a specific type of thing that you're trying to test for. Like if you have a test for SARS, for instance, if you get a positive from that test, you definitely have SARS. Sorry. So in our plagiar example, we can now apply these terms to what we learned. Can anybody tell me what the sensitivity of plagiar was? 90. And what about the specificity? 80. Yes, good. 80, right? So we had 80, we had 90, and we ended up with 65.8. All right. So let's put these on the chart here, and we can see. And the prevalence is what percentage of your population has the problem that you're talking about, right? Okay, here's an imager link with the chart on there, so if you want to load it up on your computer, because it's useful to have. Before I move on to the meat and potatoes of this talk, does anybody have a question about this stuff? Good. Wow, you've either all been following or given up. All right. All right, good. So this is the main statistical concept I want to talk about. It sounds to me like the title of a self-help book that you'd find in a magical herb shop or something, The Power of Positive Predictions, but it's a real thing. It comes from statistics, and it's the probability that if you get a positive, it's a true positive. Or in terms that we'll all understand, it's the probability if you get paged at 3 a.m. that you actually have to get out of bed and fix something. So we care about this number. We care really hard about positive predictive value because it affects our quality of life, it affects our bottom line, and so it's important to think about. So imagine you have a service with 99% up, or 3 nines uptime, 99.9, right? And you have a Nagios check for it that's doing 99% spec and sense. So you might think, oh, that's pretty good, 99, all right. Well, I'm gonna disappoint you. Here's a more abstract version. So we remember it was the dark green over the dark blue plus the dark green that we had to calculate. Sorry, are we taking a picture of that? I'm gonna go back. So let's calculate the probability that at any given time this probe runs, we're going to get a true positive. Well, we gave ourselves the numbers. It's the probability that something's actually wrong times the probability that we'll detect something's wrong. So we end up with 0.099%, or about 1 in 1,000. So 1 in 1,000 times this probe runs, we're going to get a true positive. Okay, so we can calculate the dark blue too, the false positives. That's just the probability that nothing's wrong times the probability that we'll incorrectly think everything's broken and the sky's falling. And we end up with 1 in 100. I am getting a bad feeling about this. I don't know about you. It turns out that the positive predictive value here is 9.1%. So if you get paged by this probe, there's only a 1 in 10 chance that something's actually wrong. You wouldn't think that, right? That's unintuitive. Let's think about why it's so terrible for our business. We want our checks. So think about car alarms, right? This is some Romanian picture or Serbian picture. So car alarms. So raise your hand if when you hear a car alarm outside the window, you run and check to see if somebody's stealing a car. Oh, we got one. All right, one good Samaritan here. Raise your hand if you even know what your own car alarm sounds like. Right? So I notice my hand is not up. If you know what your own car alarm sounds like, it's probably because it accidentally went off. Car alarms go off for all sorts of terrible reasons that have nothing to do with car theft. They go off because of electronic failures, mechanical failures, out here probably earthquakes, asteroid impacts in Russia, all sort of things that are not somebody stealing your car, right? In fact, when I lived in Boston, I could hardly sleep without the sound of car alarms going off outside my window. So car alarms, you see, have a very low specificity. They'll go off for just about anything. They're highly sensitive, but they're useless because you don't believe them. We want instead our alarms to be more like smoke alarms. When a commercial smoke alarm, not a residential one, but a commercial one goes off, chances are either somebody set it off intentionally, either to test it or because they're an asshole, or there's smoke, right? When you hear the smoke alarm go off in your office, you don't I don't put my headphones back in and keep working and think, oh, it's probably fine. I don't go ask around to see, hey, do you guys smell smoke? I don't think there's a fire. Is this bogus? I'm just gonna hang out. No, you get your ass to the door, you go downstairs, and you wait for the fire truck. So you wait for the alarm to go off. And that's what we need to have. We need highly sensitive and specific probes. And you saw on the chart earlier that they are not mutually exclusive. But sometimes we like to treat them like they are, so I have some practical advice about, well, it's not super practical, but I have some advice about dealing with them in the correct way, right? So why do we have such noisy checks? Why do our checks end up being so noisy all the time? Well, if you've ever had to be alerted to an outage by your boss, or even worse, by an angry customer, you know that in the wake of these horribly embarrassing things that hurt our bottom line and outages that we didn't know about because we weren't monitoring hard enough, we go tune our thresholds, right? We say, okay, well, I didn't catch this outage because my threshold wasn't low enough, so I need to lower it, and then I'm going to catch the outage next time. Well, yeah, you should try to get a more sensitive, obviously your check isn't sensitive enough. But there's a problem when your check only has one threshold. So let's say you're monitoring some API with a response time threshold, and you say, and you can raise or lower this response time threshold. If you lower it really far over to the left over here, then you're going to catch all the outages for sure. But you're also going to catch a lot of things that are not outages, right? And you're going to stop believing the check. Okay, what happens if you raise your threshold way over to the right over there? Well, suddenly you're getting a lot more sleep, which is great, but also everything is exploding and you don't even know. So, and you can't escape from this line. There's only one dimension here. So what I would argue is that specificity and sensitivity are not mutually exclusive, like we sometimes think if our checks are a little bit too lazy, like mine almost always are. You need more knobs to turn, more degrees of freedom in your Nagios probes to be able to tweak this and turn that line into a surface. So you can move around these, you can move around and tweak both of these parameters without necessarily sacrificing one for the other. So one of the really useful tools that you can use is hysteresis, which is a term I learned from my EE friends, but that everybody talks about here, where you depend on previous behavior of the system, right? So you can do state machines where the probe knows what it was happening last time it was checked, and it'll switch in states after a few times of something happening. You can do time series analysis, like we were talking about earlier, where you can say like only alert if if this response time is more than 10% higher than it's been in the last 5 weeks or something. Now you have two knobs if you do that, right? You can tweak the 10% knob down to 5 or up to 20, or you can tweak the 5 weeks knob down to a week or out to a year. And you don't have to be constantly sacrificing sleep for catching all the outages. But you're not doing worse at catching outages, right? Another thing to keep in mind is that as your service gets more reliable, you need to keep updating your checks and making them more specific. And here's why. I can show you on the graph. Right? So as my service gets more reliable, my uptime is going to go up, right? And that means the blue section is going to get fatter, and the green section is going to get thinner. Well, remember, the green was in the numerator, and the blue was in the denominator. The green was too, but let's not talk about that. Turns out, if we do this, suddenly our positive predictive value jumped down from 65.8 to 33.3. And nothing happened. All that happened is our service got better. And suddenly our probes are way, way, way worse. So as your service gets more and more reliable, you need to make sure that you are tweaking not just the probes to get better at catching outages, but also to get better at catching non-outages. It's very important. And the last piece of thing, thanks Dan, that I want to talk about here is that a lot of Nagios configs conflate the problems of determining whether there is a problem and identifying what that problem is. So you'll see a lot of times you might have, say you're monitoring a service behind Apache, you might have probes for the number of Apache processes, you might have another probe for the amount of swap that Apache is using, maybe the median response time, maybe the requests per second. So you got 4 probes for this service, right? Well, Baron Schwartz says that you should only you should only alert on whether work is getting done. That's what you care about. You don't care how many Apache processes there are. If there are 0 Apache processes running, but your site's still up, great. You found a magic web serving state machine, but that's great. You don't have to wake anybody up for that. They can all celebrate tomorrow morning. So, in reality, it could be like somebody switched to Nginx and didn't tell anybody, or we moved servers and that server's down now, or your UDP packets are getting lost. Any of these things could happen, won't affect whether your site's up. So count those out. Those are gone now. Those aren't detecting problems. Those are identifying problems. Once you combine these 2 last ones into a single check, now you only have 1 probe for your service, and it is going to catch your outages. If you have an outage, this last probe is going to catch it. I don't care how many Apache processes you have running. So what I would like to see emerge is a piece of software that monitors services, not hosts, just services, that helps you do this separation between detection and diagnosis. So maybe detect whether there is a problem, and then if there is, shoot off a bunch of diagnostic probes, come back and feed that information to the person on call. But I don't have to page him if swap is high. And the other thing I'd like to see is that same product be able to track the signal-to-noise ratio, be able to track the positive predictive value of your checks over time, probably via manual input. I know that sounds horrible, but I can't think of a better way to do it right now. So that you can find the bad ones and make them better. Here's some links. I can't talk about all of them. Last one, though, is a piece of software called BISCheck, which is kind of like a Nagios replacement, but it has a lot of built-in tools for hysteresis, for time series analysis, adaptive monitoring. But I'll put these slides up, and you can check them out later. And I want to thank Tufik for reminding me about cat pictures. I almost forgot to put a cat picture in my presentation. There's when I was packing for Monitorama. Yeah, I know, awe. And come talk to me. I'd love to chat about this stuff. I will talk your ear off about it. Thanks. We have time for 1 or 2 questions if anybody wants to raise their hand. I can't see if anybody has their hand up. Probably not. Yeah? Oh, go ahead.
Is it foolish to manually try to tweak that stuff over time? How much do you need to automate tweaking of that?
That's an interesting question. So the question was, is it foolish to, is it a good idea to try to automate the tweaking of your thresholds, of the turning of your many knobs, so that you don't have to go do the manual analysis yourself? I'd like to see something do it effectively, but I think that the only way that I have found that really works so far is to mess with the knobs yourself. Because it's really hard to, if I had a piece of software that could immediately detect whether something's a false positive automatically, then I would just use that to monitor, right? I wouldn't have to go check the signal-to-noise ratio because the signal-to-noise ratio would be 100%. So you sort of have to go back afterward. The most effective thing, and I'd like to hear from anybody else if they have a better idea, but the most effective thing I've found is to go back afterward and talk about whether there was actually an outage and whether you can make the check better if there wasn't. Anybody else? No? All right, cool.